All right, and so now let's have a picture of our subrectangles with decimals here using the right Riemann sum. So on my decimals, once again, the interval is from 0 to 1 right here, and which I completely hide away all of the numerical labels, but 0 is here, so 0.25 is here, 0.5 is here, 0.75 is here, and 1 is here. See, all of these are points here. They're all being labeled there. Okay. So that's just to convince the viewer about those. And so now, after getting all of those, okay, but this time we are going with the right endpoint. So for the first interval, so now I'm going to instantly put on all of the sub-rectangles using the right endpoint rule. All right, so my right endpoint rule is here. And let me maybe zoom it out a little bit so it can show the complete view right there. All right, so now here's our picture. Okay, so the first rectangle is here, where the height is determined to be f at 0.25, and that's why I have a height being not too big, right? Not too high right here. But then in the end, all of these rectangles are above our curve here, just like how it's shown on the board earlier. Of course, forgive me that when I'm drawing that on the board, and I can never complete with machines here in terms of doing that. See? But so all of the rectangles are being a little bit above. And so the area that we're finding, is the area in between the curve, shaded between the curve and the x-axis here, and from 0 to 1. But you can now see that the actual blue area obtained by accumulating the areas of the sub-rectangles, or in the end it created an area in blue here that's a little bit above our designated area that we're looking for. And that's the reason why, back to what I said earlier about the actual area that we're aiming at can only for now be approximated by the answer from R4. And again, R4 is the sum that we call it, the sum that we call it specifically the Riemann sum. But we obtain that Riemann sum by picking the right endpoint on each subinterval. Okay? And so now, at this point right here, anyone viewing this video is still having a very long journey, but there's a reason why I'm doing this. We have not seen the actual calculation yet, okay? But now I can tell anyone the actual area that's between the curve here I'm drawing, okay? Between the bent curve here and the x-axis from 0 to 1, that area is indeed, I'm talking about precisely. So precisely that area is a 1/3, okay? And a 1/3 in decimal, if we're using any kind of calculator, it gives us a 0.3333 repeating. And so we will get to that point where we understand how we get this exact answer. But I mentioned that here for a reason, because you can see that left endpoint rule. So now let me head on the other board of mine right there. Left endpoint rule. I found only, again, according to the calculation we have had earlier, 0.21875. Okay, that's left endpoint using 4 subrectangles. And then right endpoint Riemann sum using 4 subrectangles is 0.46875. So neither one of these is the area that I pointed out. The exact area is, as I said earlier, is either a 1/3. I mean, is calculated as a 1/3. So how can we reach to that exact area? Okay, and that's the next question, because in the way how it is right now, then it will permanently stay as an approximate. Okay, so here's the plan. So, and you just have to admire how clever, how smart the mathematicians in the past that they have done for us. And at this point, actually, I'm not going to redraw the picture here. I'm going to use decimals to illustrate the idea here. Okay, and so let me quickly prepare my screen on the computer screen here. All right, so here we go. So same graph, same partition for now. We broke the interval from 0 to 1 into 4 subintervals. Okay, but now we weren't happy with the result we've had, because this result here as the left Riemann sum, obtained as a left Riemann sum, we were a little bit under. Okay, and actually the picture right now makes it look quite under, because we had some pretty obvious, pretty trivial white space here. Okay, so we weren't satisfied with that. Now, using the right Riemann sum as a choice, then we had some value above. We got an accumulation that's above, and not only above by a little, we were quite above the actual area, because the actual area is here, okay, between the curve in red and the x-axis. And so now this is what I'll do. And this is, I'm only pointing out the plan that mathematicians in the past have done, and I have to always admit this has never been my idea. If it was me, the first one doing that. Okay, so I was just learning it like anybody else in the beginning. But the idea now is that now I want anyone to pay attention to this interval right here, to the whole total interval, and see what's going to happen. Okay, so this is what will happen. All right, so all of a sudden, see, same total interval from 0 to 1. Okay, from 0 to 1. Okay, that same interval. But now I'm going to break that down. Look at what happened here. Let's try to make that into 6 subintervals. See if we get any better results right here. Okay, so again, 6 subintervals and equal width again. So let me swing back to the board here, and let's set out with so our next plan, same functions, and the interval here is still between 0 and 1. We know that the area is a 1/3. I'm going to have to note it here. But then this is what I'm doing. The whole interval of the graph. See, according to the picture you have seen with decimals, it's going to be something like this. We break it down into 6 subintervals. Okay, but why not making it equal width? And so with the 6 subintervals here, this is how, so it's a delta x here, it's a delta x here, and supposedly they're all equal to one another. And so that means I can just call that the delta x value anywhere here, any of these subintervals is the same width, being, how about ending point being 1, subtract initial point or beginning point being 0, but I used 6 subrectangle. And so in that way, I'm going to divide that by 6. And so my answer here is a 1/6. At this point, I highly recommend using the fraction here for our setup right here, because if we're using decimal here, it's going to give a very lengthy decimal, because 1/6 is having a repeating decimal similar to the 1/3 right there. Okay, and so let's keep that delta x right here. The width for each of our subintervals here is a 1/6. So once again, anyone here is having a second look at how we obtain the delta x. It's all due to the reason that we broke it down into equal width. Okay, and so now my picture is going to be a little challenging for me to do a hand sketch here. So I'm going to bring up decimals here. All right, so for decimals, if we are going with 6 subintervals like this, decimal is going to have a very good picture for us. So this left endpoint, let's stay with left endpoint for now. So, and actually we're going to investigate both. So for now, let's start out with left endpoint. First interval is here. Okay, left endpoint is of course that point. For second interval, left endpoint is here for second interval. And then for third subintervals, the left endpoint is this point right here. So now let me quickly bring up the picture. It's just that decimals is limited in the sense that I can't, for now, maybe I haven't found that way of doing that, but I can't bring up the rectangles one by one yet, but I can only show it all in one after I prepare them. So this is the left Riemann sum to illustrate. All right, so now you can see it agrees just like how we have done the earlier activity when it was 4 subintervals. So now on each of the interval here, see, if we randomly pick one interval or one rectangle now, right? Then the height came out by substituting in the left endpoint of the current interval into the function to obtain the height. Okay. So now having the picture right here in front of you, let's really do the math right here. Now we're ready. I'm gonna still keep the picture here together with my board so that anyone can see that. All right. So we have the picture there together with what I'm doing. So now all I'm doing is I'm gonna create the partition, just like how I highly recommended earlier. And so with the picture here on the graphing space, okay, 1 is here. I'm trying to make it super big, and then my curve is going out kind of like that. Okay, so that last point is here. Okay, and then right, so if 0 is here, then the first partition point has to be a 1,6. Okay, and then the next one here is a 2,6, namely, but 2,6 is the same as a 1/3. Okay, and then this is a 3,6, which is a 1/2. Okay, and this is a 4,6, which is a 2/3, and this is a 5,6 right here. Okay, so those are our partition points. Okay, so now having the picture here, we can move on one by one. So how about first rectangle is right here. Okay, and I hope anyone can see that through the small screen. So with my first rectangle is right here. So I'm gonna bring it over to the other board to nail down the calculation for. And so the approximate I'm doing here is f of 0, because 0 is the left endpoint on my first interval, and the picture is still there with you. Okay, and we're multiplying that with the width 1/6. Okay, and so that's the area for the first rectangle. Now I'm moving over to the next rectangle right here. So I'm summing it up, and so now with my next rectangle. All right, so the next rectangle is here. It's for a second interval, the left endpoint is here at 1/6. Okay, or on my other board, it's this point is my left endpoint for second interval. Okay, second subinterval. So I can also label. I should have also done that in the beginning here. This is interval number 1. So the red marker is just the label of the interval. Number 1, number 2, number 3, number 4, number 5, and number 6. Okay, so the red ink, or just the label for the interval number. Okay, and so now on my other board, so now getting that area of the rectangle, and you're still seeing that on the picture, then it's now going to be f at 1/6, but multiply with 1/6 being the width. So height times width, height times width. Okay, and again, so for the third interval. Okay, so again, the picture is here. Okay, and with that picture there, third interval is here. So the height came out from that left endpoint on the current interval, and so the current interval is, see, first, second, third. So on the current interval, this is our left endpoint, and so now we can make it to the next one right here. All right, f at So that value there is going to be a 1/3, and I'm going to multiply that with width 1/6. Okay, and so now, as anyone pretty sure about where I'm going, I'm going to start picking up the pace for this particular one right here, because I don't want to waste your time watching slow steps right here. So 1, 2, 3, fourth interval now is going to be f at 1/2 times, so this is the left endpoint on my fourth interval, times the width 1/6. Okay, and in my next step, I'm going to add in the next line down here, and now I'm at my fifth interval. So f of 2/3, okay, times the 1/6 being the width. So this is the height, this is the width, right? And the last one here is f of 5/6, and multiply with 1/6. Height times width again. Okay, and so now the work we're doing here is now, it's a Riemann sum, but using left endpoint rule. So that's what the capital L is for. It's a Riemann sum. Okay, and even though, again, I did not explain what exactly a Riemann sum is yet, but you can start picking up the ideas from here. And when I make that transition into the actual formal definition, you will understand a much more in a much more solid way. But this is 6 subintervals, so I'm going to indicate subscript 6 here. Okay, and so now for laying down the calculation setup right here, and L6 is going to, so f of 0 is f square, and maybe let me start doing things a little more clever here. But see, throughout all of these terms here, we have common factors. So algebraically, we can factor out all of the 1/6 here as one factor. It's just all of your dx right here, I mean all of your delta x, all of your widths is one common factor. And now inside of that, I'm going to open a parentheses. It's going to save my lengthy writing, and I don't have to jump into too many lines right here. So f of 0 is going to give me, and that's what remains in parentheses here. So now I'm going to have 0 square, but I don't have to worry about multiplying with 1/6 because that was pulled out as common factor here. Then I'm moving on to the next one, being f of 1/6. So 1/6 square, okay? And the third one, so first rectangle, second height, right? Third height now is going to be f at 1/3. So it's 1/3 square, because our function is still the square function, plus, and this is now 1/2 square, and so that's my fourth one. My fifth one here is a 2/3 square, and my last one here is a 5/6 square, and I'm going to close that closing brackets. So this setup here should be good for us to come up with a final numerical answer. But all that here is once again L6. Okay, the right endpoint rule, I mean the Riemann sum using left endpoint rule. I apologize for accidentally saying the right endpoint. That's going to come later. So, and using sub intervals. Okay, so this time my answer, according to what Desmos gave me, L6 came out being, let me write it here, L6 came out being 0.254629, and a lot longer, and I'm not even rounding it. Okay, and this is definitely not the area. The area that we're sketching here, that we're tentatively getting as the aim here, that area, as I mentioned earlier, is 1/3, is 0.3333 in decimal, if anyone prefer writing it that way. But at least we came closer. The earlier answer, when it was L4, it was 0.21 something, and now we went a little bit higher, we went a little bit up by breaking it into more subintervals. Okay, so start recognizing for yourself a strategy. For now, I call it a strategy to improve our accuracy. But in the end, any of these, L6 or even L10 or whatever, it's only an approximate. So we still did not get the exact area. This is only an approximate. So now I can say, let's roll back to the point where we did not, where I did not tell the answer of the area yet. Then without knowing that exact answer I mentioned, then the area is approximate by L6. It's a better approximation. The area can be approximate by L6. Okay, and now you can see that right on the picture here, that you see the area here, the amount of white space being left out. It's still the area that we're accumulating after accumulating all the little subrectangles here is still below the actual area we're finding, of course. So it was 0.2546 and a lot longer, but it's still under 0.3333. And so that's why we still have these little white spaces here. But admittedly now the amount of white spaces reduced. Okay, the amount of white spaces reduced. Okay, so now we've got L6. And so now in that way I can even pick up the pace even a little more. So let's try out with the right endpoint rule. Okay, so we still know that tentatively our area will be a 1/3. We still have not found, your professor teaching here still have not shown you, still has not shown you how to get that area yet. But you can see that as we increase the number of subintervals, same total interval, but increasing the subintervals, the number of subintervals means we have to break it down into smaller the width here. And that's why it's such a challenge for me now to draw that with a hand sketch, and so I have to turn over to use the technology and show that in front of you. But let's now use the right endpoints. So on each of my interval here, you see first interval, I can pick right endpoints being 1/6. The second interval, 1/3 is the right endpoint, and so on and so on. And so let me have some time preparing my screen here, and I'll quickly bring it on the board. All right, so here we go. Here's our graph again. I completely cleared out all of the left endpoint demonstration. But now still, the interval from 0 to 1 is broken down, is chopped down to 6 subintervals as our plan right here. And so now let's look at the right endpoint, or the right Riemann sum with 6 subintervals. See, 1, 2, 3, 4, 5, 6 subintervals, and they're all equal widths. So a couple preliminary steps right here. Each of the subrectangle here is again, so delta x we know is 1 minus 0, final point, subtract initial point, the total interval's length. That's what it is, 1 minus 0 divided by 6, and that gives me a 1/6. So each of these little space here, the red numerical label is only just a label. The space between each of these, any of these two consecutive points, is a 1 space. I mean, is a 1/6. Okay, so now I'm going to clear out the board, and we're going to start setting up for here. And we have all the picture here, and we can even pick up the pace a little better, because I've had all of that partition points that you have seen earlier, and hopefully anyone viewing the video has also taken note on the partition points. And if you haven't, you can always roll back to the earlier point of this video and take note on that. Okay, but so now for first rectangle, and remember I mentioned that we're doing right endpoint this time. So first rectangle is here. Okay, and I hope my mouse cursor in a small screen can still point out for you where the first rectangle is. But right endpoint now is going to have to be that point to be the first, to be right endpoint on the first rectangle. So in that way, the area we want to find, height, can be found by f of 1/6 actually. So the height is f of 1/6. I'm going to multiply with the width, 1/6. Okay, and then for second rectangle, right endpoint allow me to once again use the mouse to point it out on the computer screen here. This is our rectangle number 2, or subinterval number 2 right here. So right endpoint is here, and from there we substitute that value into the function, and that value itself is what? 0.3333, which is a 1/3. And so now if I substitute that into the function, we will get the height only being this much, and drawing over we have a rectangle. And so the width here remains 1/6, but the height is whatever come out as f of 1/3 right there. And so now in my picture, f of 1/3 times 1/6. Okay, that's for the rectangle. And now the third rectangle, f of 1/2 times 1/6. Okay, and then the next one, 1, 2, 3. We've had 3 down so far. The fourth one here, f of 2/3, okay, times 1/6. Okay, and now I'm at the fifth one. I'm going to need to add with f of 5/6. Okay, multiply with 1/6. So this is the right endpoint. The value, the spots, the x equal 5/6 right here. That's the right endpoint on my fifth interval. And then the last one here is going to be f at 1. Okay, multiply with 1/6. Okay, and so the total sum here is accumulation that we call, it's a Riemann sum, but using the right endpoint rule. So capital R, I used 6 sub intervals this time. So it's capital R6. That's what right Riemann sum with 6 sub intervals is for, or generally an R6 or an R4. That's what it means. Okay, and so now laying down the math before we actually put in the final calculation value. Now again, notice that we have a common factor 1/6 here. So for saving space purpose, I'm going to pull out the 1/6, and it's also the way that's less calculation for us. So 1/6 here, and now I'm going to look at 1/6 square. The right endpoint substituted into the function. The function itself, remind yourself, it's a square function. Okay, plus, and now 1/3 square plus, now 1/2 square plus 2/3 square, okay, plus, and then I have a 5/6 here, squared, and I have the last one here is 1 square, and close my parentheses. And so that's what I'm going to be calculating, and whatever will come out from this calculation, it's going to be our R6 value. Okay, so now calculation of mine that came out from decimals gave me R6 here calculated to be, all right, so 0.42129.6, and a lot longer. Okay, and again, we already knew, I told anyone viewing this video lesson, the area, the exact area we're trying to achieve is 1/3. It's not this area. However, roll back to the point, when I didn't tell you that, then we can use this as the approximate to that area. And so now you can see in the picture that's still on your screen right now, you see the blue area is still being above the actual area that we're looking at, the blue area that came out from accumulating all of the little rectangle areas. But in the end, it came closer. It came closer. So now let me quickly do a comparison. So now if we stay completely on decimals right here, let me put the decimals on full screen. Okay, let me put decimals now on full screen, and let me switch between, let's go back to when it was 4 subrectangles. Okay, so when it was 4 subrectangles, the amount of overestimates was a lot more than now. Now when we have 6 sub intervals, then each one of these gets shrunk down, and then so the amount of overestimates is getting less. So the overall blue area here comes closer to our designated area between the curve in red and the x-axis here horizontally. Okay, and so in that way, now again I'm saying that pretend that you still didn't know the answer of the actual area, then you can always say that the area that we're trying to achieve is approximately, or is approximated by R6. Okay, it's R6, neither R6 or L6 is the answer, but the area can be approximated by those depending on how precise we want, we want for any of that. Okay. All right, and so now let me put decimals on screen right here, and we're gonna do a pretty interactive work right here to show everybody the idea. And I'm not expecting much I'm not expecting anyone to do a calculation along the way yet. It's only a demonstration, a graphical demonstration for now. Okay, so let me clear out this picture. Let's roll back to the left Riemann sum right here, using 6 rectangles. So we started our activity with 4 sub-intervals, and then we changed to 6 sub-intervals, and we got better approximate, So think about it. What can it be as a plan, as an excellent strategy to keep improving our accuracy? Because none of the work we have done so far has gotten us the exact area, and I'm still leaving that on the board here. The area is already, I told anyone it's 1/3, but no matter what we tried so far, we still didn't get to that 1/3. Okay, so let me bring up this activity right here, and so now this is my decimal, and that I shows some of the other extra stuff right here. The graph is still here. Okay, the graph is still here, but I showed on all of the controls on the left-hand side panel here, so that you can see. I want to show a little bit of an interactive. So Ln right here is indicating that the left endpoint Riemann sum with n sub-interval. So what's n? N in my control here is currently 6. So that means right now it's L6. And the same here right now, I'm using 6 sub-intervals. So it's indicating here that this is R6. So if we go with L6, then our answer was this answer right here. That I hope it's on your own computer screen. It's not too small to read, but that was exactly the answer I've had earlier written down on the board. It was a lot longer. And then this is R6 right here for 6 sub-rectangle, even though I'm only showing the left Riemann sum picture right now. Okay, so now let me do this. Same interval. Let me also show the interval. See, our function here is set up to be the x squared function. Our interval from a equal to 0, and our ending of the interval is at 1. That's what I set up for decimals like that. Okay, and so now using the left Riemann sum, let me do this, and the amount for left Riemann sum is still being indicated here at the bottom of our screen here a little bit. So I'm gonna, this time, I have to admit, I'm not happy with only 6 sub-intervals, because the answer is still not close enough with 1/3. So let's do this, and this is the part where we can start enjoying decimal right here. I'm gonna increase. And so as I'm dragging this slider right here to increase the number of sub-intervals, I'm not expecting any viewers to do this instantly, because it takes a lot of time on your own work to do this. But decimals can do that, 1,000 times faster. So why not relying on decimals? And let's investigate how fascinating this is. Okay, so I'm gonna drag the slider, and so notice how these area changes. See, right now I stop at 20 sub-intervals, and we're even going to have a hard time counting. But you can pause the video and count. There really are 20 sub-intervals in here, okay, in between, and there are under. But look at the amount of white spaces now. They keep getting less and less and less, and the total accumulation of all of these rectangle areas is getting closer to our destination. And I'm using that term, the destination. Our destination is 1/3, and we keep getting closer to that. And the strategy to get there is keep increasing the number of sub-intervals. Keep getting n get larger. Keep getting n larger and larger. Okay? And so see, and to convince you, the calculation that shows instantly, that's done instantly by the decimal is right here. When we're at 20 sub-intervals, we are at the area 0.3, close enough now, 0.30875, still a little under, but see, we start hitting to the 0.3. Okay, and so let's even go further. So I'm gonna roll to, what about, I want to keep changing that to, how about, notice how my rectangle changed. All right, and so now when I go to about 80 sub-intervals, even decimals is having a hard time showing all the little white spaces, because it comes so close now to the actual area. Okay, and now it's a good time to start noticing ahead anyway, in the same total interval from 0 to 1, admittedly. What do you think will happen? And I only want to raise this question without anyone really have to answering me, but start putting in mind, what is the consequence as we keep increasing the number of subintervals within one same fixed interval from 0 to 1 here. Look at what happened to the width of each interval, and you can see that your own math skill is good enough for you to understand this. Okay, and now the calculation for all so this is what n equals 80, so that means this is L80 right here. The left endpoint Riemann sum at with 80 subintervals is 0.327. It's already much closer to 0.3333 already. But still, I'm not happy. So let's go with how about the 260? So the picture is nearly exactly the area we're looking at. Okay, and can anybody viewing this video really tell the difference between any two adjacent tick marks anymore? And the width here is very tiny. That's all I can say, right? And let's look at the L. Well, how many rectangles do we do here? 260. So L260 is this much. So we keep getting better and better and getting closer and closer to 0.3333. Okay, and that's the idea right there. And then so for just a little bit fun for viewers right here. So as I drag and I try to aim to see somewhere at 270, decimals cannot display all that, so it just assume all that area is there. But with the calculation, it's still showing slightly off. And actually, all right, and see the value changes very little bit here, even when we get to that extreme. Okay, so now let's roll back to the earlier point. All right, or for short, I'll just go back to 4 spaces. 4 subintervals. Let's switch over to the right endpoints to see what happened. All right, so right endpoints are these 4 subintervals. That's how it looked like in our earlier activity. And now the answer was, I'm going to have to scroll this up a little bit to display. So this is R4 here, because right now currently I'm using 4 subintervals. And we switch over just now, we calculated with 6 subintervals. And so this is what we've had right there, and I wrote it down earlier. Okay, and now from this point on, as I said, it got closer to 0.333. This answer we've had here got closer to 0.333, but I'm not happy enough, so let's keep dragging it. Let's go to, how about, see, 30 subintervals. See, if you want, you can go ahead and pause the video and count the number of subintervals here. Decimals that's awesome in terms of making really good precise graphs like that. Okay, and you can see that now the Rn or 30 at this point is down to only 0.3 something. So earlier, within what we were doing the calculation, and it was 0.4 something, way above 0.3. But now we start hitting down to within the 0.3s right there, and we are a lot closer. And look at the amount of overestimates. It's already a lot shrunk here. And so now I'm going to keep increasing the number of subintervals. So how about let's go to like 100. Okay, and same rules here. I trigger your understanding with that question I've had earlier. Think about the impact of one total interval in the beginning, but we try to keep increasing the number of subintervals. And what's going to happen to the amount of dx right here in each of our subintervals? And you will keep that in mind for your own like that. Okay, and so now the total, this is n equals 100 subintervals. So this is Rn or 100 being this value at that value right there. Okay, and so I can keep increasing more, and to a certain point that decimals can't display the difference in the triangles in the rectangles anymore. It shows an actual area as a picture. But see, if you're looking at the actual calculation, it's still here. Okay, all right, so now we are ready for really introducing, and it's still it's a little better introduction to Riemann sum compared to what I introduced earlier, but it's still not the formal introduction of the Riemann sum yet. Maybe right now it's just a final conclusion of what we've been calling the Riemann sum, but I still haven't gotten to that core understanding of what a Riemann sum is yet. Okay, so Now I'm going to need to erase my picture. All right, so it looks like generality. I mean, as a generality, then let n here be the number, right? The number of subinterval. The number of subintervals inside of our interval, inside of our total interval. So how about in the interval from a to b? Our problem was that famous function x squared and inside between, so a is 0 and b is 1. But generally speaking, n is the number of subintervals inside of that. And so any of our, so Ln right here, that symbol Ln is being regarded as the left, or maybe let me write in red ink right here. So L is called the left the left Riemann sum. Okay, with now more specifically n subintervals. All right, so that's what it is. Okay, and the idea was just now, see, we break it down, and of course we stay with equal widths right here. So for simplicity for our life right here, delta x equals just b minus a over n. The final point of the interval minus the beginning point divided by the number of subintervals that we're looking for. Okay, and so on the other hand, as a conclusion we've drawn out about these symbols right here, then Rn is regarded as, I mean, as a name, we call that it's the right Riemann sum. Okay, and we're doing that with, of course, n subintervals. Okay, so now left Riemann sums means, so we, back to what I was saying earlier, we broke our interval into n equal width subintervals, and on each of those intervals, we pick the left endpoint on each interval to create the rectangle. To create a rectangle, so the height of rectangle is being determined by the function evaluated at the left endpoint on that current subinterval, and that's why it's called left Riemann sum. Okay, and then in the on the other hand, so these two so far is just a choice of work right here, and I will clarify what I mean by a choice right here, because obviously if we stop even with the n5, I mean n10 or n100, within what we can do right here, within what our calculation can do, the n10 or n20, I shouldn't say 100 earlier, it's a little too much, we have to leave 100 for decimals, but even we go with R10 or L10 or R20 with L20 and doing the things that with manual calculation, we still didn't get to the actual area, and they're all quite some difference. So how can I call that a choice? I will clarify that later. But so the right Riemann sum with n subintervals means that we break our intervals from a to b, our total interval, into n subintervals, equal width again. But on each subinterval, we're going to pick the right endpoints and substitute that into the function. Okay, and then from that we obtain the height. So the height, according to the right endpoints rule for Riemann sum, then the height is obtained by the function value at the right endpoint on the current interval given. Okay, and so now allow me to explain what I meant, to clarify what I meant earlier by anytime you are doing this. Anytime you are approximating the area, the actual area of inside between the curve and the x-axis, and inside an interval from a start to an end of an interval like this, and doing either a right endpoint, I mean a left endpoint Riemann sum or a right end Riemann sum, it's a choice. Why am I saying that? Because as a matter of fact, we want we want to find a way to get to the exact area. And so in that way, in the end, ultimately, using left endpoint or right endpoint, we all in the end try to improve our approximate by keep getting more ends and more ends. Again, I'm repeating, starting out with either left endpoint or right endpoint, it's okay, but our ultimate goal is to reach to the actual area. So the only way of doing that, doesn't matter if you're using left endpoint rule or right endpoint rule, you're always going to want to eventually keep increasing the number of subintervals so that you can keep getting better and better to the approximate. And that's why I said it's really just a choice right there. And in any choice, for the traditional calculus students, and which many of you in viewing this video can also be on that path right there, then we're going to have to learn the idea of we're going to really formally sit down and do a couple problems where we really experiment letting n goes to keep being more and more n and more n, okay, and keep increasing infinitely the number of n right there so that we can achieve the exact answer, okay. And that's the idea of and that's the reason why I said any of these is just a choice right now, okay. All right, and so now to get viewers and students of mine a really good hang of it, instead of just watching what I'm doing up here, let's now get into some examples, because you have learned enough theories behind the scenes now. So let's look at our example 1. All right, so in our example 1, I want to approximate. So let's approximate the area between f of x equals x squared function again, okay. So we want to approximate the area between f of x and the x-axis. So between that and the x-axis, and then okay, this time I'm going to switch the interval a little bit. Same curve, same function x squared. It's still such a fascinating world to work with that. So, but now I'm going to go from -1 to 2. All right. So as a picture, quickly as a picture, it's going to look like this. The area that we're trying to, and so since my picture is so small, I'm going to keep swinging back and forth between what's on the board here and what's with decimals right there. So I'm mostly going to use the decimals for the picture. But see, 2 is about here. So we got about 2 areas like this. So cumulatively, this is our area. That's what we're trying to find. That's the part I'm shading, okay? And for that, but we want to use, so my wording here is stating clearly approximate that area, see, between the curve and the x-axis, right, from -1 to 2, right here. But that's just the description of the problem. Now let me swing over to the other board. I'm going to need to erase. All right, so how about question A right here? So we want to approximate, but now using, how about L4? Okay, this is something that we can all do with our papers and pencil and with a calculator. We don't need decimals for this. We don't need a nice graphing calculator for this. Okay, so now as a starting step, again, the interval starts at -1 and ends at 2. That's our interval. Okay, and then the symbol says using L4, left Riemann sum using 4 subintervals. Okay, or eventually 4 subrectangles. All right, and so let me now bring up the picture with decimals before we really heading out for the calculation there. I'm going to take a moment to prepare my screen with decimals. All right, so here we go. Here's my decimals. So this time on my computer screen here, this is the picture of our graph in that interval from -1 is here. Okay, -1 to 2. So -1 is here and 2 is here. Okay, and we're going to break it down into 4 subintervals. So 1, 2, 3, 4, and they're all equal widths right here. Okay, so if we are constructing using L4, the left Riemann sum illustration picture will look as following. That's the picture right here. Okay, because in each of the subinterval, we're going to say for the first subinterval from the left to the right. First subinterval, we're going to pick the left endpoint. That's what it is. And so this is -1. For second subinterval or subinterval number 2, we're going to pick the left endpoint again, because that's the rule we want to do for this problem, for these problems right here. Okay, so now in that way, I'm going to swing back to my board and sketch down the partition chart of this, all of these partition points, anywhere from -1 to 2 right here. Okay, so because that's a common good habit to practice right here. So the interval this time start out at -1 and ending at 2. We don't need to draw the graph over it, because that we can leave for decimals. Equal width is what we're using. So delta x here, we can also do a little bit prepping step here ahead of time. 2 is the final end of our interval. Okay, minus -1 over 4 subintervals. Okay, so that gives us here a 3/4 or a 0.75. Okay, and so now 4 subintervals is here. All right, so now we can do a little calculation. So we add a 3/4 over to this, right? That gets me a -1/4 right here. That's my partition point, or a -0.25. If anyone is more comfortable with the fraction, with decimals. And then right here, okay, so it's a 0.5 right here, or let me write that first in fraction. So it's 1/2, okay, or 0.5. All right, and then we're going to add another 3/4 to that. Okay, so that gives me 5/4. All right, and then that's going to be 1.25, and the last one here is going to be 2, and of course that's what it is. Okay, and so that's our partition point right there. So for us to know, so that means now on the picture that we're having, on the picture that we're looking at right here, then the area of the first rectangle here is going to be found by, and let me also mix that screen with this decimal screen here with my board here for us all to see and work together with that. Okay, and so for the first rectangle, left end point is this point at -1. So now maybe I need to, I just write it down, but since we're having short space here, I'm going to have to erase that. Okay, so it's going to be, the height is f of -1, and we multiply with the width being 3/4. Okay, and then that takes care of the first rectangle, and this is something we can do. and then plus, and now for the rectangle number 2 right here in the second interval, second subinterval, then it's going to be, so left endpoint is going to be negative 0.25, which is negative 1/4 right there. So f at negative 1/4, so negative 1/4 itself is the left endpoint. See, right here, negative 1/4. Okay, so negative 0.25 or negative 1/4. That's the left endpoint of this second interval right there in our work. So in that way, to get the height of that rectangle, I'm going to substitute left endpoint into the function to get the height. Then I'm going to multiply with the width, 1/4. Okay, and then for the third rectangle or third subinterval, I'm going to get the height again by using the left endpoint. This time as a 1/2 in my picture right there. Okay, and multiply that with, and actually I've been making a mistake here. It's not a 1/4 for this width here. It's actually a 3/4. And so now I'm going to also multiply with 3/4 here as our width. And for the last one here, the left endpoint is, that is a 5/4. I'm a little more comfortable with fractions. So, and then 3 multiply with 3/4 the width. Okay, and so this is tentatively L4 right there. So we want to use this L4 calculation to approximate our area, being the area is inside of this. Okay, the area is inside of that right there. Okay, and so now back in my picture, I mean in my work right here, then again, similar to what I've shared earlier, we got common factor. So it's just an approach that now it's completely on papers and pencil. I'm going to factor out that common factor 3/4. So 3/4 being factored out. So now our function is still that famous x squared function. So negative 1 is the substituted value. I'm going to square that. Next value is a negative 1/4. So negative 1/4, I'm going to square that. Next third sub-rectangle, I'm going to look at 1/2 square. And the last one here is a 5/4 square. Okay, and then now that's my value eventually for L4 right there. Okay, so my calculation for L4 came out to be, so my calculation for L4 came out to be, so now L4 was 2.15625 right here. Okay, sorry about that. I keep switching back and forth with my computer screen right there. But so again, this is not the actual area. So the actual area, let me quickly hide away all right. So the actual area is that area between, okay, let me quickly do a, all right. So it took me a little bit to create instantly the graphing area right now, but the actual area we are doing is this area on the graph. And this area is more than, really more, a little bit more than just the area by the rectangle. Okay, so just by the rectangle we have something like this, and there is a lot of white space left out, and a little bit, some of those are above, but the amount of being above, being over here is way less than that, and altogether it's not the actual area we're doing. Okay, the actual area we're doing is here. All right, and so now in that way, all I can say here is that our real area, which is at this point I don't know what that is. the area now is approximated by 2.15625, and that's now our answer. We have approximated the area, okay, using L4, and L4 is 2.15625. Okay, all right, so now same problem. Let's look at part B right here. So same exact example, same interval, same function given. How about let's use R4? Okay, and so again, same interval. So 4 subintervals. The only difference now is we want to use a right Riemann sum with 4 subintervals. So in that way, now think about. Let me quickly put that on the graph again so that you will have a good picture. Okay, now I'm going to put away the left endpoint. Let's look at the right endpoint. All right. So for the right endpoint this time, you see, first interval, we are using the right end of the first interval, so it gives me the height right here. Second interval, the right end is here. Third interval, the right end is here. Okay, and so that's why it creates the rectangle over. Okay? And fourth interval, the right end is here. And so now I'm going to once again remind anyone about these partition points right here. So these are our partition points. And then very shortly I'm going to have to erase that. Okay, -1 is here, 2 is here. So at that point here is a -1/4 because each of the little dx here, delta x there, I mean, is a 3/4 space. And so this is here a 1/2. Okay, and this is here a 5/4. All right, and so in decimals, -0.25, this is +0.5, and this is a 1.25. Okay, so that's this is the quick sketch of all of the partition points right there. I highly recommend doing this, but it's not really, it's never been a hard requirement actually. Okay, but it helps big time. All right, so now, so using R4 over here. Okay, first rectangle. Then I'm looking at f of -1/4 and multiplying that with 3/4. Second interval or second rectangle, f at 1/2. I'm multiplying that with 3/4, the width of the rectangle. And then for the third rectangle, the height is going to be found by f at 5/4 and multiplying that with the width 3/4. And the last one, I run a little bit short of line, so f at 2 would multiply with the width 3/4. And the picture is still there with any one of you viewing the video. All right, so now as far as the actual math to be laid down, R4 will equal the setup as following. Now again, I know there's common factors, so I'm going to go ahead and factor out the 3/4. Okay, first term is a -1/4 all square plus, now gives me 1/2 square because we're still working with the square function. And now I'm going to add 5/4 all square. And then the last term here is 2 square. And none of these steps I have to multiply with the 3/4 anymore because that was a common factor and I factor it all out in front. And so now R4 here, I'm getting ready for the final calculation. All right, so my final calculation with decimals, it showed me R4 equals 4.40625. Okay, and again, This is not the actual area, but at least we can use this as an approximate to our area. So you can also say that the area, on the other hand, outside of L4, you can approximate that area by R4. So area can be also approximately 4.40625. And that's the kind of problem we're doing here.